Hi, this is the 8581 control award video. I will first explain the different aspects of the robot that we programmed, and then show our full autonomous at the end. So in the code, the robot is abstracted into three different subsystems: the wobble grabber, the shooting subsystem, and the drivetrain. The wobble grabber class declares 2 servos to grip the wobble goal, 2 limit switches, and 1 wobble motor. The limit switches are placed so we can prevent the wobble grabber from moving too far up or too far down during teleop, and thus preventing the belt on the grabber from being ruined. The wobble motor is a special class which encapsulates FTC's own DC motor class. It adds extra functionality like motion profiling and a PIDF controller, which helps ensure the wobble grabber is in the exact position we need it to be, and aids in keeping the movement from being too jerky. Here's some footage of us running the test for the wobble motor class. Next up, we have the shooter subsystem. The shooter subsystem contains all the elements of the robot that deal with the collection and the shooting of rings. During autonomous and teleop, all of these elements act in tandem through a finite state machine. The intake class contains a simple motor. The kicker and lift class contains simple servos, as well as their respective positions they need to go to. And the shooter class contains a motor, which uses the rev's internal PID loop to maintain a constant velocity. Lastly, there is the drivetrain. In past years, we've had issues in autonomous making the robot drive in the same way every time. To resolve this, we decided to use Roadrunner, a motion planning library maintained by Acme Robotics designed specifically for FTC. Roadrunner uses PID loops and motion profiling, and also takes into consideration the kinematics of the robot's drivetrain to help with consistent autonomous driving. It also helps us make more complex maneuvers during autonomous, like turning and moving forward at the same time. Alongside all of our subsystems, we have a USB camera attached to the back so we can detect the rings in auto. We use an open source vision library called OpenCV, partially because we've used it in the past, but mostly because the options provided by FIRST are too slow and too bloated. To detect the number of rings, we sum up the number of yellow pixels on the screen, and compare that sum with a series of thresholds to see how many rings there are. It's fairly basic, but considering this is the only usage for the camera during auto, it would probably be over-engineering to do otherwise. Throughout this video, you've also been shown a video of a tool we use called FTC Dashboard. This is a tool also maintained by Acme Robotics, which allows teams to display telemetry graphs and even a field map on their computer while the robot runs. We've extensively used this, especially when tuning PID gains. With all that being said, here is our full 71-point auto. With that, I hope you enjoyed the 8581 Control Award video.